Hello students. Can you see the compass on the screen? Do you see any deflection in the needle? Oh, it's dark. So first, let's switch on the table lamp. Now it's better. But wait, what just happened to the compass needle? Yes, it has been deflected. Was this caused by the table lamp when it was put on? Let's do it again. Put on and off the table lamp again. What did you observe? Each time the lamp is put on, the compass needle shows deflection, and when the lamp is put off, the needle returns to its original position. What do you think? Why the compass needle deflects each time the table lamp is put on? Well, actually, when the lamp is put on, the connecting wire begins to behave like a magnet because of the magnetic effect of electricity. This in turn causes deflection of the compass needle. If the wire behaves like a magnet, then it should have a magnetic field. So now you must be wondering, what will be the pattern of magnetic field generated by a current passing through a straight conductor? Let's investigate this with an activity and try to map the magnetic field around a straight conductor. Insert the straight conductor through a cardboard sheet. Now connect the conductor to a simple circuit consisting of a switch, a rheostat, an ammeter, and a battery. Students, you know that a rheostat is a device which regulates the resistance. The top end of the conductor is connected to the positive terminal of the battery. Sprinkle some iron fillings on the cardboard and see what happens. Nothing happens right now because the circuit is off. Now switch on the circuit. Ensure that the wire passing through the cardboard is vertically straight and perpendicular to the cardboard. You can see that the iron fillings get arranged into concentric circles around the straight conductor when current passes through it. So did you get your answer, students? Yes, you got it right. When the wire is straight, the pattern of the magnetic field is circular. That is, magnetic field lines are in concentric circles around the conductor with their common center at the axis of the conductor. You must have observed that the magnetic field is perpendicular to the conductor. Now, do field lines caused by a straight conductor have direction? Yes. Let us verify this with the help of a compass. Place a compass at a point, say P, on one of the magnetic field lines. Observe the direction of the needle. The direction of the north pole of the compass needle would give the direction of the field lines produced by the electric current through the straight wire at point P, which is shown by an arrow. What will happen to the deflection of the needle if the current flow is in the reverse direction? The deflection of the compass also reverses, indicating that the direction of the magnetic field lines changes with the change in the direction of the current. Can you think of a simple way of finding out the direction of the magnetic field lines if you know the direction of the current? Yes, we can find it with the help of right-hand thumb rule. Imagine you are holding a current-carrying straight conductor in your right hand, such that the thumb points towards the direction of current. Then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field. If the direction of the current changes, the direction of the magnetic field lines will also get reversed. In other words, the direction of magnetic field lines will either be clockwise or anti-clockwise. This rule is known as right-hand thumb rule. So far, we have kept the amount of current constant. What will happen if the amount of current is changed? Let's see. Let us now keep the position of the compass fixed so that the distance of the compass from the conductor is constant. If you switch on the circuit, the compass needle gets deflected. Adjust the rheostat to reduce the amount of current. The compass needle shows lesser deflection than before. Now adjust the rheostat such that the amount of current increases in the conductor. You will observe that the deflection of the needle increases. So we can say that the strength of magnetic field decreases when the current decreases, and the strength of magnetic field increases when the current increases. Now, what happens to the deflection of the needle if compass is moved away from the conductor, keeping the current constant? To find out the impact, shift the compass to a further point from the conductor, say from point P to Q. What change do you observe? You will observe that the deflection of the needle decreases. Thus, the strength of the magnetic field produced by a given current in a conductor decreases as the distance of compass from the conductor increases. You will also notice that the concentric circles representing the magnetic field lines around a current carrying straight wire become larger and larger as we move away from it, which means that the strength of magnetic field is decreasing. Now observe the deflection of the needle when the compass is moved closer to the conductor. The deflection of the needle again starts increasing. Thus, the strength of magnetic field produced by a given current in a conductor increases as the distance of compass from the conductor decreases. You will also notice that the concentric circles representing the magnetic field lines around a current carrying straight wire become smaller as we move closer to it, which means that the strength of magnetic field is increasing. In other words, the strength of magnetic field is inversely proportional to the distance from the magnet. You know, students, the motor in a toy car, bullet train, aircraft, or spaceship uses similar magnetic effects. So students, what we have learned in this video? The direction of magnetic field line depends on the direction of current. The right hand thumb rule gives a simple way to find it out. The strength of the magnetic field created by a current carrying wire at any point depends on, first, the amount of current in the wire, second, the distance of the point from the wire. The magnetic field is stronger near the current carrying wire and it diminishes as you go away from the wire. In next video, we will see magnetic field due to current passing through a circular loop, and magnetic field due to a current passing through a solenoid.